So we've got a couple of people here from the CE development team. Would you like to just introduce yourself and let everybody know, first of all, who you are and what it is that you do in the CE team?
Okay. I'm Sue Lowe. I'm a developer on the Windows CE team. I work on the kernel and file system and also performance and performance tools.
Okay, and who are you?
Hi, my name is Bor-Ming Hsieh. I'm the lead kernel developer for Windows CE. I've been working on Windows CE kernel for more than 6 years. And recently we did a complete rewrite of the kernel for Windows CE 6.
Okay, so this is the third time that we've re-architected the kernel, right? We had Windows CE version 1.0, which was the first build of the kernel, right the way through to CE 2.12. And then we did some major work for CE 3 to provide real-time into the operating system. And now with CE 6, we're doing another rewrite.
Yes.
So what's new and what's changed and what's different with CE 6?
So the most important change for CE 6, basically we break the 32 process, 32 meg virtual memory limit for Windows CE. In pre-CE 6 version of CE, all the processes will share the same address space. So, and since each process needs a certain amount of virtual memory available, so the number of processes multiplied by the amount of virtual memory has to be, it is a constant, so we cannot support like greater than 32 meg of VM or greater than 32 processes. For CE6, we moved to a complete different model, which is resembled to most of the modern operating system, where every process has its own virtual memory space, 2 gig of virtual memory space, while all the processes share the same kernel address space above the 2 gig level.
Okay, so why are we making these changes to the operating system? What was wrong with 32 meg and 32 processes?
Well, the 32 meg virtual memory limit was introduced in 1990, where the target device we're aiming at is like 2 meg of memory and 2 meg of flash.
Right.
And 32 meg sounds a lot.
Sure.
And in that environment, 32 process sound a lot too. Now things get evolving until recently. When we were hitting this 32 meg of virtual memory boundary very easily. In recent Windows Mobile releases, we're facing out of virtual memory problem like daily, and 32 process limit also poses a big issue for OEM like Auto PC, where they actually have a lot more than 32 processes.
Okay, so you're basically talking about open devices.
Yes.
Devices that you can load additional applications or services onto.
Yes.
Right. Okay, so how do you even get started with changing an architecture that's been around for 10 years to a completely new and different architecture?
Let me put it this way: the upper level management says that we need to change the operating system. So they sent me off to a completely different schedule. Basically, started writing the operating system where everybody was still working on the existing operating system. So I basically started writing kernel like writing a CE6 kernel like a year ahead of everybody else start working on the CE6 kernel.
Mm-hmm. So how do you decide what that new architecture is going to look like, and how do you then start implementing that? Where does the idea come from for, in effect, rebuilding CE from the ground up?
Okay, so we have a team of architects, John Eldridge and Mark Miller and the rest of the kernel teams, that we get together discussing what the architecture is going to look like about weekly. And it usually comes this way that I propose based on what I read from the desktop code, or based on my understanding of the operating system. I proposed an architecture, and then we come in and discuss with the architect, and everybody will give opinion of this is good, that is good, this is bad, that is bad, and eventually we come to agreement, and that will be the architecture we decided. And for the implementation, it actually starts with simulation.
Mhm.
So believe it or not, the first Yamazaki virtual memory is running on Windows CE 5.
Okay.
Basically, it is a standalone program, dealing with all the virtual memory, simulating all the virtual memory operation, and basically, I need verifying that all these operations do exactly what I expect it to do, and then after that, I can plug that virtual memory into a new memory architecture. Otherwise, if virtual memory doesn't work, and if the kernel boot up and virtual memory doesn't work, practically it's impossible to debug.
Okay. Okay. So, can one of you draw out the differences between the memory model and how that looks on CE5 and what the new memory model looks like on CE6?
That would probably require me drawing something.
Sure.
So let's start with the CE5. So in CE5, for the 4 gig of virtual space from 0 to so above this is kernel.
Uh-huh.
Below this, the second gig here is map file. Basically, you can think of it as the shared memory for all the processes. And then below this, sorry, I tend to like to draw this because if I draw this way, it becomes too thin. And then below this, basically, it is cut into 32 meg slot.
Okay.
Each process on a slot, actually. And slot zero is special. Basically, it is used for current running process. So the 32 slot actually is spent over there. This one doesn't count as a slot. And every process runs in its own individual address space. So based on this picture, you can see that any process, if you want to access any process's memory at any given time, as long as you have the address to this individual slot, you can see it.
Okay. So isn't there a lot of work needed to move from one current running process to another running process? So if a process that's currently in slot 0 makes an API call, doesn't that potentially force a chain of other processes to swap into slot 0?
Yes. So for CE, when API call, a thread makes an API call by migrating itself into the API server to carry out the operation. So yes, if you call into, for example, call into file system call into GUI. So every time when you swap process, you need to make slot 0 pointing to the new process that you call into.
Isn't that costly in terms of time?
Theoretically, it's not that costly without protection because usually it's just a few pointers that you initialize. But if you take protection into account, it becomes it can become pretty costly because depending on architectures, you may have to zero several memory that you access. You need to invalidate the page table or page directory for a certain process once you gain or lose a protection.
Okay.
Yes.
So realistically, what is the difference between kernel mode and user mode on CE5?
Realistically, user mode basically just the only difference between user mode and kernel mode on CE5 is just one. For one, you can access anywhere in this map. For the other, you can only access this part in this map,
Okay.
in the address map. Well, it's practically the same for any operating system. Basically, if you want to access kernel mode address, you must be in kernel mode. User mode address, you can access anytime you want. Of course, there are some protection mechanism in CE file, like set proc permission is required in order for you to access other processes' memory. But given enough privilege, yes, you can do that.
Okay. So what about CE6? What does CE6 look like?
All right. Now, CE6 is, well, the big picture is still the same. Kernel mode, still kernel mode. However, you can think of it as user mode is actually individual processes. There are several. Every individual process has its own 2 gig of address space.
Okay.
But by looking at this, you see, you can say, let's say this is process 1, process 2, process 3, process 4, process 5, process 6. By looking at this, you can see that only one process is visible at any given time.
Mm-hmm.
You are not allowed to see, when process 1 is in place, where you don't see any address space of the other processes.
So does that mean that I can't read or write to the memory address space of other running processes on C6?
Unless you marshal the argument, or either by virtual copy, or you do copy out, or you use read process memory or write process memory. There's no direct access given a pointer, and you can get to the other process right away.
Okay. Okay. So it sounds like set proc permissions doesn't exist anymore?
No, it doesn't exist. It doesn't exist anymore because it's not going to work in this architecture.
Okay. So each process is running inside of a 2 gigabyte virtual address space.
Yes.
What does the inside of that virtual address space look like?
Okay, so inside this, you can think of this as a DLL base. All the DLL loaded from here.
And what is that baseline?
This is basically 1 gig line.
So the process itself runs from base memory up to 1 gig?
Yes. DLL all loaded from here, and from, actually there's another line over here at the third at 1.5 gig line, and then there's another line here, 7,000 line. Between this, we call it is the share heap. Basically, this is user mode read-only, kernel mode read-write heap, which is used in GUI mostly for performance enhancement, where GUI can store some structure over there where user mode window application can just read it and determine things.
Do you have an example of what that might be?
For example, get window long. Let's take one for example. Probably this is not a good example, but in my imagination, given the window pointer is some here, over here, and then you say, I want to read something from the window structure, like get window long, and then you can just read it from there without actually calling into GUI to do it.
Okay.
Things like that. Between 6 zillion and 7 zillion, this is our RAM-back map file. Theoretically, we don't need this, but we introduce this basically for backward compatibility reason.
So what goes in there?
So only RAM-backed memory map file go there.
Okay.
So let me just try to.
Let me interrupt for a
Yes.
second. RAM-backed means that it's a memory map file without actually a file underneath it. It's kind of a misnomer, but RAM-backed map file is really just a memory buffer that you open with the Create File Mapping API.
Okay. Why might you do that? Why would I create this memory map file?
Applications use it, people use it to share memory between processes because it gives you a convenient, you can give a name to this memory buffer and then another process can open it using that name. and then you can share the buffer between the two processes.
Okay.
And I should let Bor-Ming continue to explain why this was, for backwards compatibility reasons, forced to be inside this memory range.
Sure.
Okay, so for CE6, because all the map files were in fixed address, so there are many map file implementations that actually store pointers around inside the map file, saying, I get this, I get a pointer and use it. And then different processes, for example, process 1 and process 2, both accessing this map file, and they can use this pointer in CE6, they use this pointer and it works just fine.
Okay.
For a real map file implementation in CE6, actually, when you create a map file, there's no guarantee that two process, the same map file in two processes may reside in different places, different virtual address. So if you store a pointer in here, the code will never work.
Mm-hmm.
So in order to try to be backward compatible with that, we figure that for a file backed, basically if it is a memory map file, for a real file, if it is a file backed map file, practically you cannot store any pointer in there, because if you store pointer in there, next time you reload the file, there's no guarantee it's going to be at the same location that file is loaded. So this type of thing would, in our based on our observation, this type of access pattern would never occur in a file-backed memory map file. So we decided that for RAM-backed memory map file, we try to map them at the same address across all the processes.
Okay.
This is basically why it is there.
Okay. So theoretically, how many processes can I run on CE6? We were limited to 32 processes on CE5. What about CE6?
Well, basically as much as your memory can limit. That's what I would say. But I mean, one of our tests actually run, I think it's 2,600 processes.
Wow.
In one of its tests. Although that process probably doesn't do a lot of things, but
sure.
But it actually creates 200.
So the architecture,
uh-huh.
the architecture of CE6 supports up to how many?
Architecture is support by. It's not a hard limit. It's actually a limit by our handle table implementation that we only support 64K handles inside kernel. So every process requires at least 2 handles.
Yeah.
So theoretical limit is around 32K, but I wouldn't be surprised that it's 16K. But I think 32K or 16K really doesn't matter in this particular scenario.
Right. People want more than 32.
I don't think so.
More than 32 processes.
Oh yeah.
Yeah.
As long as it's reasonable amount, I think it makes sense. I think running 100 processes or 200, I think shouldn't have any issue.
Okay. So on CE version 5, which is this kind of thing set over here on the left-hand side, many of those slots at the lower area of memory were taken up by parts of the operating system itself. Things like GUIs and device driver manager and other things.
Uh-huh.
So what happens to those in CE6?
We actually move file system, device manager, and GUI into kernel.
What is GUI?
GUI, graphical, basically it's the graphical window events server. I think basically it's the windowing system. You can think of this way.
Okay. So on desktop Windows, there are 3 core components, GDI, kernel, and user. Why don't we have the same 3 components in CE? Wouldn't that make sense for application compatibility? Wouldn't I then be able to take applications from the desktop and run them on CE?
I think you're asking something that I don't completely understand. But I mean, how you're talking about on the desktop side, you have 3 major components: kernel, GDI, and user.
And user, yeah. So even a simple application like Notepad will import from those 3 things, right?
Yes.
So
and I believe those 3 were just, if you think about it, they were just stumps. basically application, when they want to make into kernel, make to GDI, or make into user, I don't know what is user. Basically, application, this, I think this, you can think of this as our core DLL. I think. I'm just
my assumption is that the combination of core DLL and GUIs is, in effect, kernel, GDI, and user. So why do we have two separate things, like core DLL and GUIs, rather than having the same three named components?
GUI is actually the implementation of things.
Okay.
Not the core DLL is just the thunk. And this is the real implementation. Whether GUI want to reside in the user side or in the kernel side really is just a implementation decision we make. But from application's point of view, they always, for Windows CE, any application link with core DLL, period.
Okay.
Yes, and it doesn't have to link. It doesn't have a three different DLL to link to. You have one.
Right.
It has one, and that DLL doesn't contain the implementation. Actually, as a matter of fact, other than like CRT is in there, in anything other than CRT, practically, were just a thunk into the kernel, and then kernel will dispatch that into individual drivers, or it can even be a user mode driver, user mode server, that you make an API into kernel dispatch it to other server.
Okay, so we're moving file system, device driver manager, GUIs down into the kernel.
Uh-huh.
Why are we doing that? If we've got up to 32,000 processes now being supported, why isn't file sys, device driver manager, and GUIs just up in user space?
Basically, the major reason is performance. Anything in kernel is a lot faster. Anything become a user mode server becomes slower.
Why is that?
Well, think of it this way. If you call it to kernel while this particular application is in place, inside kernel he can access anything here. So there is no data marshalling required. Any pointer passed into kernel can access it right there. Of course, we need to do some validation, but we can access it right there.
Okay.
However, if you want to call into another process, a memory here we need to make this visible to this other process.
Okay.
Okay, so there are a lot of data marshalling need to occur during this API call.
Okay.
Right.
So how expensive is it now to swap out one process for another?
Swapping out process is actually very cheap. It's just a pointer. You just set a pointer to different process. That's pretty much it. Okay, but the thing is, swapping process usually involve in especially V4 or V5, when you switch process, because their cache is virtual tag, when you switch process, we need to invalidate all the caches. That's the expensive part of it. And for other architecture like x86, it's actually pretty cheap. Basically, we just flush we just replace the CR3, the page directory mapping. Just change the page directory mapping, and we're done.
Okay. So what about real time? Does any of this architecture change affect the real time behavior of the operating system?
So we continue to be hard real time. There is no extra. That we did not introduce any new unbounded call in CE6.
Okay. All right. So one of the things you mentioned just a few minutes ago is user mode drivers. If the device driver manager is now in kernel space, why do I have a kernel space drivers and user space drivers? What's the difference between them?
Well, for robustness, security reason, you want to move because let me try to back it up a little bit. Drivers come in two flavors. One is when the device ships, it comes with the device where OEM has it, they test it completely, they know that it works, and they're very performance aware, saying I want this thing to go fast. In which case they put it into kernel mode. But there's another class of driver where, for example, you plug in a car, it pop up dialog asking to install driver, things like that.
So like a third-party USB driver
yes.
of some kind.
For those, Depending on how the OEM want it to be. If OEM say, well, this driver is signed with my certificate or whatever, so it can load into kernel mode. Yeah, he can load into kernel mode. Otherwise, we can restrict it to we load it. It can be loaded into user mode where it will not be able to trash random kernel component or basically kill the device or steal things.
Right. So on CE version 5, we had a couple of interesting calls, like set K mode to get into kernel mode, and we had set proc permissions. If these don't exist anymore, and I've got a user mode driver, then how does the user mode driver touch memory that's owned by the kernel, or deal with interrupts, or touch the memory of other processes?
User mode driver are not allowed to call set K mode anymore. So if the driver was touching the kernel mode address directly, either the driver needs to be rewrite or that driver will have to be a kernel mode driver. For a well-behaved driver that calls, for example, MMIO space or that it registers itself as a driver, and the registry specify what type of interrupt, what type of physical address they need to access. Most of the user mode driver code will be routed through device manager. Device manager, based on the registry setting, determine whether the call should succeed or not. For example, if the registry says this particular user mode driver have access to physical address A through B, and then the driver when the driver is loaded, it tries to do a virtual copy for physical address from A to B. The device manager will let it succeed.
Okay.
However, if it tries to do a virtual copy via any other place or call map IO space from any other IO space where it's not specified in the registry, the device manager would deny the call.
So that, yeah.
Can I actually interrupt for a second? So one of the things that I thought maybe I should explain also is why would someone actually want to call set K mode or set proc permissions, and what were they doing and why, and what's different in the new OS. So if suppose that this application needs to call a driver, the thread will actually jump into, say, device exe, which has the driver running in it. And since the process space is always visible, what really happens is this thread gains permission to access data inside of device exe when the application calls it. And while it's inside device exe, that thread continues to have permission to access the memory space inside the application.
Okay.
But if this driver needs to do something asynchronous with the buffer that was inside the application, the drive, so say some thread inside device needs to access that application, this thread doesn't inherently have permission to touch the memory owned by that application.
Right.
So the thread calls set proc permissions to get the get permission to the application's memory space here. And then the thread operates on the buffer directly inside the application. It's actually similar in our new model, where if the application, which is running down here, passes a buffer into device, while that thread's running, the thread, that buffer, this process is still mapped into the user mode address space. And the thread inside of the kernel address space here can continue to, the thread that jumped can continue to access the address space, because while that thread's running, its owner process continues to be mapped here.
Okay, so.
But if we go to an asynchronous thread here inside of the kernel, it's possible that while that thread's running, some other process starts for a second and then gets rescheduled out, and the virtual address space changes. That's not the original process anymore. So this thread needs to do something to marshal that buffer so that it can access it inside the kernel here without actually relying on that process continuing to be mapped. And that's why we have some new functions. There is CE alloc asynchronous buffer, some other, we call them marshalling helper functions, which replace the functionality that people used set K mode and set proc permissions for.
Right. So what is the difference between a user mode driver and a kernel mode driver in terms of capabilities and what it can do?
We tried very hard to make them almost the same, so that you could write code once and have it work in both places, and that OEMs could make decisions to move drivers one place or another without having major headaches and having to rewrite code. The differences are limited to things like we restrict so that only kernel mode code can do certain things, like he said, virtual copy from any address space you want. You can't do that in user mode. The only other cases are around asynchronous return to callers. So if a user mode driver needs to asynchronously write back to a caller address space, we don't necessarily allow asynchronous access to other processes
Right.
from user mode.
So one of the things that Bor-Ming mentioned was that it's possible for you to, if you're a device driver, to through the registry set the memory range that you should have access to. If I wanted to be a badly behaved driver and try and get access to everything, could I not just set the registry and just get everything I wanted?
And that registry is supposed to be protected, and depending on the OEM, depending on the signing of the installation program, it may not have access to the registry. So I guess let me put it this way: someone will have to sign the installer in order for it to be able to put things in the registry.
Yeah,
Okay.
the area of the registry where it looks, the access to that is also restricted. So you have to have access to even modify that registry in order to get access to the buffer that.
Okay. So if we jump over to kernel mode drivers for a second, if I'm living in the kernel, surely I don't have access to some of these user mode services like Windows and dialog boxes and those kind of things. So I can't really throw up a dialog to a user or a message box or something when I'm in kernel space. So what do I do about that?
Actually, that restriction's not about access. It's just that we didn't want to run all of that inside of the kernel for stability reasons.
Okay.
So we moved all of the UI elements. We purposefully omitted them from the kernel so that kernel mode code couldn't use UI because we didn't want to load all of that stuff into the kernel and induce any kind of instability from that.
Okay. So how does a kernel mode driver or code that's running inside of the kernel display UI? Something like a networking driver that needs to.
Yeah, so
we
actually introduced a new API called CE get user param, I think. Basically, it basically can be called from a kernel mode driver, or actually from any driver. From any driver can say, I want to do this. And the argument to that is the DLL name and the function name. So basically what we did is actually create a process, the current implementation is creating a user mode driver, okay, and load the DLL, find that function, and call that function, and then return a value back to the caller. In which case, you can do all your UI in that DLL
in user space.
Yeah, in user space.
Right. So what about application compatibility? How compatible are applications that were written for CE5 to run on CE6?
Well, so far, I think we're more than 90%, right?
I don't know any numbers, but in general, well-behaved applications should not have any problems and not require any kind of rebuild. There are certain, if the applications are doing things like virtual copying from addresses all over the place, they may not be able to continue. And there are certain scenarios around things like the fact that these memory map files were accessed at the same address in every process that broke in the new VM. So like, for example, in CE5 and before, if you made a read-write memory map file here, then it was always read-write. And if you tried to map a read-only view to that file, it was actually read-write still. Mm-hmm. And if you wrote code that then wrote to that view, it would work fine in CE5. But if you did the same thing in your process in CE6, that memory map file view would actually be read-only like you asked for, and then when you read-write, or when you write to it, you'll get an exception. So there are some scenarios, if you're badly behaved, we did our best to support even badly behaved applications, but we did break backward compatibility in some areas where we thought it wouldn't hit too many people and that the cost was high for supporting backwards.
Okay. So how long, just as an estimate, how long would it take me as an OEM to move my existing CE5 image over to CE6? Let's talk about BSP.
So, well, the BSP story. So BSP is two things: OAL and drivers. The OAL changed a little bit. We changed the OAL so that it doesn't link directly to the kernel like it used to in C5. And there's a little bit of work, not a lot, that has to go into rebuilding your OAL in a different way. That we've actually documented fairly well, and it's we've done examples where we do it in 10 minutes in front of people, and it's really minimal.
So why would you do that? Why would you break the OAL out?
The main reason is updatability.
Uh-huh.
So now an OEM could, get a new update from Microsoft with a new kernel and not have to rebuild their OAL into that update. They could, ship that out to their customers without having to package the two together.
Right.
And also, just it helps us the same way. Like, if I make a change to the kernel, I can rebuild it without having to use platform code to.
No, well, there's actually a major advantage with this setting. For example, we have on the field we have a device, right? We have a device that we have the flat list directory, and we know that something wrong. And before, if we try to instrument the kernel and try to load it into the device, remake image, it's not possible because we don't have the OEM code or OEM library to link the kernel with.
Mm-hmm.
Today, we can just grab this flat release directory, drop in the new kernel DLL, remake the image, then I got a new image with my instrumented kernel.
Okay.
And that's advantage number one. Number two, there are devices that is like practically almost all the same, except a little, very few changes in basically some changes in the OAL. For example, all the drivers are the same. Just OAL, for example, the BSP startup or initialization code, there's a little changes. In those scenarios, basically you only need a release directory, and you can drop different OAL into it. It become an image for a different device.
Right.
So going back to your question about how costly is it to port a BSP,
Mm-hmm.
Also related to this OAL kernel change is OEMs in some cases had discovered that if they would write SC underscore to the front of a function, that they could call functions that we didn't really intend to be called from the OAL.
Okay.
And now in CE6, with this separation of DLLs, we also have a very strict and limited set of functions that can be called from the OAL. So if people had written their OAL to do a lot of internal kernel stuff from the OAL, it may take more work to restructure that to use kernel mode drivers or something like that. So as long as there wasn't a lot of interdependency on calling internal kernel functions from the OAL, it should be relatively easy and straightforward to port to a new to CE6.
Okay.
Now, when it comes to drivers, there is some work, for the most part, for drivers that restructuring, like I said, instead of using set K mode and set proc permissions, now you'll have to modify it to use some of our marshalling helper functions to get access to the memory that you need. If your driver doesn't use any embedded pointers, it may actually be a really simple task to port a driver. If it has embedded pointers, things like that are passed to the in-buff as an ioctal, you may need to modify them slightly to use the new marshalling helpers. So it may not necessarily be like straight binary compatibility from the driver. It might take a slight amount of development.
Okay. So what are the advantages, just to wrap up, what do you think the advantages are for an OEM to use CE6?
Well, they get the benefit of our virtual memory model, and it gets rid of a lot of nasty virtual memory shortage problems that people running into.
And actually, I believe, based on our some profiling data, most of the kernel mode driver is a lot faster. So, for example, I know that our networking code is faster, Basically, our network performance is better. And the Yamazaki kernel is completely right, and we actually add a lot of things to improve the robustness, where I would say it is the most robust kernel ever for Windows CE.
Okay, that's a fantastic note to end on. Thank you both very much.
Thank you.
Thank you.